Hello everyone. In this lesson we will look at tokenization. So let's understand what is tokenization. So the input text that we give to LLM, it's in raw format and it cannot be directly consumed by the models. So we need a mechanism to convert that raw text into some numerical representation. So this process is nothing but tokenization. So there are different types of tokenization. One is simply that you can think that we will break each character of the text as a token. So each character will have a unique ID. So that is called character level tokenization. But that is not very effective since we will have individual characters does not convey any significant meaning, and the model is not able to learn much from that. So another form can be word level tokenization, where each word of the text is treated as a token. And finally we have a subword level tokenization, where it's a mix between character level and word level. So it's not so granular at the level of characters, and it also may not contain the entire word. Some of the frequently occurring and smaller words may be token themselves, but some of the words are broken down into subwords, and those are tokens. So first let's look at character level tokenization. So as the name says, each character is treated as a token. So each character will get a unique ID. Example, if we have a text hello llama, then we will break all the characters and we will assign some ID to it. So if let's say H has some ID, let's say 10, E has maybe 5. I'm just assigning some random random ID. Let's say L has 2, then this L will also have 2. So these IDs denote their ID of tokens in some dictionary. So we have some token or vocabulary in some vocabulary. So each token will have some ID. So all the L's will get the same ID. So this is a new character or a new token, so it will have a new token ID. Let's say it's 3. Then this space character will also get some ID. Let's say 7. And then again L is here, so same thing, 2, 2, maybe 1. Let's make it 15. And again this A will get 1. So you see each character is treated as token, but there are many drawbacks of this approach. First is that if you are given a character A, you are not very sure like what will be the next character, and because it carries very little information and it's hard for model to understand the underlying structure of the text if we train based on this tokenization. So we have a text and then it's passed to tokenization, and then these numerical values or IDs, and then IDs are further broken down into some embedding vectors, and then these are consumed by our LLM models. So these characters do not contain much information, and the model will not be able to learn much from this kind of tokenization. And also it requires many tokens to represent a small string. So this hello llama is pretty small string, and you see that we already have 5 and then 5, 11 tokens to represent this small string. So let's say if we had word level tokenization, then we would have just 2 tokens as compared to 11 here. So it hampers the performance as well as accuracy. So let's move to next tokenization called word level tokenization. And as the name says, each word of the text is treated as a token. For example, if we have hello llama, again we have 2 words, so we will have 2 token IDs. Let's say this is 1001 and let's say this is 20005, some random ID. So it captures more meaning per token than the characters, but it can result into very large vocabulary size. So some estimate is that for English it can go up to 500,000 of tokens, 500,000 of words in the vocabulary if we go with this approach. Because if you see, if we have let's say run, it gets some token ID, let's say 1000. If we have runs, it gets another token. So both are representing similar action, but one is runs, one is run. So it will have another token ID, maybe 1001. Similarly, if ran, running, all of these will have their own token IDs. So this way the vocabulary grows in size. So we need a mechanism to tokenize in such a fashion that we reduce the number of words tokens in the vocabulary. So all of these are similar. So this was one problem, and another is that if there are some slangs which are not very common in English vocabulary, or it was not present in the training set, and if there are some typos, let's say running, but by mistake somebody types RUMNING, it looks pretty similar to running, but this is a typo and it does not exist in the vocabulary. So it will have some special token for unknown tokens. So there may be many of these unknown tokens in the training, and also these slangs will not be there. So these are the main problems of word level tokenization. So the final one is subword tokenization, which splits text into subwords. So it captures the structure and the meaning of the text. So for example, if we have hello llama, then I am giving some random tokenization where maybe the word hello is a token in itself. Let's say assign a value of 1000 token ID. And then llama is broken into LLA and MA. So this MA starts with M, but this LLA, it starts with a space here. There may be multiple approaches to this. Sometimes they may start with some hash symbol or something else. So let's say it starts with space. So it conveys that this is the beginning of a word in the original text. So in this case, it's broken down into 3 tokens. So we will have 3 IDs, let's say 2000 and 5000, as compared to word level tokenization where we had 2 tokens. So it's a balance between character level and word level, as you can see, and it reduces the vocabulary size. So if we have run, runs, running, and many of those other words, so running may be broken into run and n maybe, and then ing or something like that. So so many of the words, so many of the verbs which end with ing, they can be broken into that verb and this ing. So this ing will appear only once in the vocabulary. If we don't have an approach like this, each word will have a corresponding ing, and so it will keep double the vocabulary size, and even double, triple, and many more times. So this approach reduces the vocabulary size, and it's also good in handling unknown words. So again, some unknown words, it can be broken into some commonly occurring tokens, into 2 tokens which are present in the vocabulary. So in this way, the number of unknown tokens will be very less in the input training or inference time. So now let's briefly run through some code example and get a feel of how this tokenization works. So let's come to our Google Colab notebook. So first of all, we will need to import auto tokenizer, and then let's try GPT-2 and see how tokenization works for GPT-2. So let's wait for a few seconds. So this runtime is connecting for the first time, so it may take some time. So now this will download the tokenizer, which is pretty small compared to the actual model. And now let's say our prompt is hello llama, and we want to print the input IDs. So in this case, it's broken down into 3 tokens. So we get 3 IDs, so we know that it's broken down into 3 tokens. But in order to see like how this happened, you need to decode these IDs. So let's decode these using tokenizer.decode, and let's print them separately in different lines. So this first ID corresponds to hello. So hello is itself a token, and then space LL and AMA. So this was tokenization for GPT-2. Now let's add a few word like let's say unhappiness, very long word, so that we get some feeling like how this long word is broken. So this time it's 5 tokens. So till this third part it remains same. Then unhappiness, again it starts with space denoting the start of word, and then happiness as a separate token. So you can see how this subword level tokenization works. So let's try some other tokenization. Let's try llama 3. So you need to give the exact path here. So for llama it's meta ll ama llama, and then we want to use llama 3. Llama 3 8 billion model. So let's run it. So you will see that it complains that you are trying to access a gated repo. So it's because it's a gated repo, and you need to accept their terms and conditions on this llama Hugging Face llama site. And once you accept that, you also need to log in with your Hugging Face token. So for that you can write so you can write login, and then you need to log in with your token. So I logged in using my token and removed the token for obvious reasons. So once you log in, you will not need to log in again. So now we have the llama 3 tokenizer, and let's see how it differs from GPT-2. So here it has a special token to denote beginning of text, and then hello, and then a space llama. So here llama is a single token, and there is a space because it's in the beginning of it's a new word. And then again UNH and happiness. So these things are similar, and but if you try it on very long sentences, you will see much more difference. So now let's get back to our lecture. So now let's look at some subword tokenization strategies. So we talked about character level, word level, and subword, and we found that subword seemed to be most optimal among these. So within subword, these are some of the most popular strategies. One is byte pair encoding. So what it does is it iteratively merges most frequent pair of characters or subwords in the text. So we will see. So let's say we have for simplicity, let's take few examples. So let's say we have words like pub, pubs, pun, and hub. Only these 4 words in our text. And let's say this pub occurs 10 times, this occurs 5 times, this occurs maybe 12 times, and this hub occurs 15 times. So it starts with this approach, byte pair encoding. It starts with all the characters. So we have a character P, we have a character U, B, and PUB is already included. So we have S, then we have PU is included, N, and then H. So it starts with individual characters. So let's say our vocabulary requirement is that we can have up to 500 words in the vocabulary, or 500 tokens, unique tokens. So we started with these characters. Then we will see what are the next pairs of characters. So P, you will see that P occurs in pubs and pun. So 10, 5, 15, 12, 27 times. So P occurred 27 times. Similarly, you can calculate for all the other characters. Now next you have to include pair of characters. So pair of characters can be PU, UB, BS. So characters which occur together, one after other. Then PU is there, UN and HU. So these are the pairs of characters. So you will see that how many times PU occurs. So PU occurs here, here, here. So again 27 times. UB occurs in here, here and here. So 15, 15, 30. So this occurs 30 times. Similarly, BS will occur just 5 times. UN will occur 12 times. HU will occur 15 times. So the most frequent pair is here UB. So next you include UB in the vocabulary, and you continue like this. So once you are exhausted with all the pairs, you will look at 3 characters and so on. So this was byte pair encoding, and it's used in GPT, GPT-2, Roberta, BART, DBERT, and maybe a few more. So second strategy is WordPiece. So it splits the word into subwords based on the frequency in training data, and it's used in BERT variations like BERT distillword, mobile word, funnel transformer, and MPNet. So this WordPiece is very similar to this. So it will start with P. P is the beginning of a word, and then it will have some special tokens, U, special tokens, special characters, B, then S, N, and H. So it works very similar to this, but instead of just directly looking at the frequency, it will look at some score. So we have to find a score for a pair. Let's say we have some hypothetical characters AB. So this score is frequency of AB divided by frequency of A multiplied by frequency of B. So this score is used instead of directly using the frequency. So this is the strategy used for WordPiece. Next we have SentencePiece. So it treats the input text as a sequence of characters and uses a unigram language model to tokenize the text. So this approach is also not very different. So here again it will grow till we reach the desired vocabulary size. In this our example it was 500. So in SentencePiece it starts with a large vocabulary. So it will take all the substrings of all the words in the text. So it will start with a vocabulary of P, U, B, S, N, H, then P, U, U, B. Then for if you look at this PUBS, it's BS, UBS, and PUB is also included. Generally we don't include the words, but since PUB is a substring of this, and then UN, UB, HU, and then all the 3-letter substrings and so on. But this was all were 3 characters or 4 characters, so we are exhausted here. But if you have some larger words, then you will have many more substrings. So here we start with a large vocabulary, and then what we do is that we need to break a word. Let's say we have U, B. So if we have a word, let's say PUB, how is it broken? How is it tokenized? So it will calculate the probability of, so it treats each of these words individually, so as a unigram, like it's not dependent on the previous tokens. So probability of P multiplied by, so it treats them independently, U, and then probability of B. So this denotes that, this probability denotes that we are tokenizing PUB as P, U and B, 3 tokens. So it will give some probability. So clearly, if let's say this initial vocabulary has a size of, let's say n, or rather here for calculating the probability, the number that will be important is total frequencies. So you need to add the frequencies. So there will be some common denominator, which will be a large number, let's say n, and then you will have some value of probability of how many times P occurs. So depending on the frequency, it will get some value. So P divided some small value, maybe let's say let's say it occurs 10 times. So 10 by, let's say n is 10,000. So 10 by 10,000 multiplied by U is occurring, let's say 5 times, 5 by 10,000. Then B is occurring, let's say 20 times, 20 by 10,000. So you see that this breaking the characters individually will result in a very low probability, since we will be dividing this large number in the denominator that many times. So most likely these will be rejected and it will get very low value, 000 maybe something. And other way would be to break it into PU and B. So in this case it will be probability of PU and B, which will be probability of PU multiplied by probability of B. So in this case it will be 10,000 will be in the denominator only 2 times. Similarly, you need to calculate probability of P and UB, and you will get some value, and you will also calculate the probability of PUB together. So depending on this thing, the words are broken into tokens. So these were the 3 strategies for sub-word level tokenization, and this SentencePiece is used in Albert, T5, MBARD, BigBARD and ExcelNet, and of course many more models. I have not listed all the models here. And so in the next lessons we will look at decoding strategies and text generation. We will also look at transformer architectures, applications of transformers in text and beyond text.